So we are continuing with eigenvectors and eigenvalues of matrices. Let me remind you, what we want to do today is we basically want to firm up the understanding of eigenvalues and eigenvectors. We're going to do a bunch of computations of specific cases where things can be interesting. So let me start by reminding you of the definition of eigenvector and eigenvalue. So given a square matrix, a non-zero vector x is an eigenvector of A if A times x equals lambda x for some lambda. We call lambda an eigenvalue of A, and lambda x an eigenvalue eigenvector pair. In Tuesday's lecture, we did some examples of specific matrices and their eigenvectors and eigenvalues, but we didn't really talk about how to find eigenvalues and eigenvectors given a matrix. So the question was, given a matrix, a square matrix A, how do we find its eigenvalues and eigenvectors? Because in our last lecture, we realized that if you just try to find the eigenvalues and eigenvectors simultaneously, you end up with a nonlinear problem to solve. So if you just literally try to find x and lambda, so trying to find lambda and x so that ax equals lambda x is a nonlinear problem. And you can see it's nonlinear because here x is the unknown. The left-hand side is certainly linear. But on the right-hand side, lambda is unknown, x is unknown. That right-hand side is quadratic. So this is a nonlinear problem. And so last time I went through various ways of rewriting the question. And it came down to ax equals lambda x for some non-zero vector x is the exact same thing as a minus lambda times the identity times x is the zero vector for some non-zero x. And that is the same thing as the determinant of a minus lambda times the identity equals 0. Because if the determinant of a minus lambda times the identity is non-zero, the only solution of this will be x is 0, the 0 vector. If the determinant of a minus lambda times the identity is 0, that means that this matrix inside is singular. That means there will be non-trivial solutions of this. So what this allowed us to realize is x is gone. Just try to find lambda. And then, once you know what lambda is, so if you were given a matrix and you figured out, you're given some 3 by 3 matrix, and you figured out its eigenvalues were 2, 9, and 7. Once you know that the eigenvalues are 2, 9, or 7, you can plug 2 in, and you're down to just solving a linear problem for x. When does a times x equal 2 times x? That's just a linear problem in x. You can solve it. Similarly, if you happen to know that lambda has to be 9, you would just plug 9 in, and then you can solve for x. Actually, what we'll do is we'll plug the eigenvalues in here. But once you know what the eigenvalues are, solving for x becomes a linear problem. And you can do it. So what we're going to be doing is, given any matrix, first find the eigenvalues, then find the eigenvectors. If you have 3 eigenvectors, you're going to have to solve 3 linear problems. Sorry, if you have 3 eigenvalues, you're going to have to solve 3 linear problems to find corresponding eigenvectors. Are there questions? Okay, so let's just start with a small example. So we have we had the linear mapping, which goes from R2 to R2, where L of x is reflect x about the line y equals 2x. And when you write down the standard matrix for this linear mapping, you get that the standard matrix is minus 3/5, 4/5, 4/5, and 3/5. And from last time, we know geometrically that lambda equals 1 and lambda equals -1 are the eigenvalues, and corresponding eigenvectors. So if lambda equals 1, then that's telling you that L of x is equal to x. That's the eigenvector problem you're trying to solve. And the only eigenvectors for that so a vector which is unchanged by this action would have to be a vector which is on this line. So x is t times 1, 2 for some non-zero t. There are infinitely many eigenvectors. An eigenvector, a vector so that you get sent to your negative. That would have to be your you have this line, and if reflecting about that line sends you to this, then you'd have to be orthogonal. This reflecting about the line gives you that, which is not the negative of the vector. The negative of this vector would be that. So the only way that the reflection is also going to be the negative is if you're orthogonal. So t was -2, 1 for some non-zero t. So we know this to be true. The question is, if we didn't have a geometric understanding, if we were just given this matrix and asked to find its eigenvalues and eigenvectors, how would we do that? So the answer is first find the eigenvalues, then find the eigenvectors. So step 1, find the eigenvalues. So we want to compute the determinant of A minus lambda times the identity. So that's the determinant of minus 3/5, 4/5, 4/5, 3/5 minus lambda 0, 0, lambda. That is the determinant of minus 3/5 minus lambda, 4/5, 4/5, 3/5 minus lambda. So that is minus 3/5 minus lambda times 3/5 minus lambda minus 16/25. And now we just do our computations. So we get minus 9/25. 3/5 lambda minus 3/5 lambda. That cancels. Plus lambda squared minus 16/25. That is lambda squared minus 25/25. Lambda squared minus 1. Now all of this is just computing a determinant. I want this determinant to equal what? 0. So this equals 0 if and only if lambda is equal to 1 or minus 1. All right, so we have finished step 1. We have found the eigenvalues. Step 2. For each eigenvalue, find its eigenvectors. So that means, so part A, lambda equals 1. Seek non-zero solutions of ax equals 1 times x. That's the same thing as seek non-zero solutions of a minus 1 times the identity times x is the 0 vector. So I need to write down an augmented matrix. So I need a minus 1 times the identity. Right in that second determinant, I have a minus lambda times the identity for general lambda. So all I need to do is just say, well, take lambda equals 1. So I have in the 1, 1 entry, I have minus 3/5 minus 1. So that's minus 3/5 minus 5/5. That's minus 3/5 minus 5/5. That's, yeah, minus 8/5. 4/5. 4/5. Now in the 2, 2 entry, I have 3/5 minus 1, because lambda equals 1. So 3/5 minus 1 is 3/5 minus 5/5 is minus 2/5. Okay, so minus 8, 4, 0, 4 minus 2, 0. 1 minus 1/2, 0. What's the second row? 0, 0, 0. Will there be a non-trivial solution? Yes, because I have a row of zeros. Because the rank is less than the size of the matrix. So this gets me that x is t over 2t, which is t times 1/2 1, which, if I want to write it more nicely, is t times 1, 2, solves the system if t is non-zero, it's an eigenvector. Are we happy? Did we get what we expected geometrically? Yes. Okay, second step. Lambda is equal to minus 1. So now I seek non-zero solutions of a minus 1 times the identity times x is the 0 vector. So that's going to be I write down an augmented matrix. So I need to subtract -1 from the diagonal. I look at the second line, that determinant. I'm going to plug lambda is -1 in there. So I'm looking at -3/5 plus 1. So that would be 2/5, 4/5, 4/5, and then 3/5 minus -1 is 3/5 plus 1 is 3/5 plus 5/5 is 8/5. So this is 2, 4, 0, 4, 8, 0 is 1, 2, 0. Second row is 0, 0, 0, which makes me happy because it means there will be non-trivial solutions. So x is t times, x is minus 2t times t, which is t times minus 2, 1, solves the system. If t is non-zero, it's an eigenvector with eigenvalue -1. Are we happy based on our geometric understanding? Yes. All right, now let's just quickly see what would have happened if we thought that lambda was equal to 2. So let's say you made a mistake when you were computing your eigenvalues. Made a mistake in step 1. So you computed your eigenvalues incorrectly. Some arithmetic mistake. Then when you're solving the linear system, you're going to have -3/5 minus 2, 4/5, 4/5, 3/5 minus 2, 0, 0, which equals, okay, 3/5, minus 3/5 minus 2/5 is minus 3/5 minus 10/5 is minus 13/5. Here I've got 4/5. Here I've got 4/5. And here I have 3/5 minus 10/5 is minus 7/5. So that's row equivalent to 13, 4, 0, 4 minus 7, 0. And this is going to have what as its reduced row echelon form? Oh, so, okay, this is a 2 by 2 one. So it's, here you saw that row 2 was a multiple of row 1. Here you saw that row 2 was a multiple of row 1. For a 2 by 2 case, you can quickly see that the only way to get a 0 in the reduced row echelon form is if this is a multiple of that. Is this a multiple of that? No. In fact, if I were to compute the determinant, do I know, is the determinant 0 or non-zero? And I don't even need to use my calculator because here I'm going to have a negative number, and then I'm going to subtract 16. So this thing has a non-zero determinant. That means it's invertible. That means its reduced row echelon form is 1, 0, 0, 1. So you get this far, and then you conclude that your eigenvector is what? 0, 0, 0. And you turn the page and you're really happy, except that your grader is just felt like you've said 0 equals 1. Because can eigenvectors ever be the 0 vector? If you ever find yourself on the verge of saying that that's an eigenvector, you need to stop. Because one of two things happened. Either you made a mistake in step 1 when you were computing the eigenvalues, or you made a mistake when doing your elementary row operations. Because if you ever get to this point without realizing you've made a mistake, there's something really wrong. Probably you're trying to work too quickly or you didn't get enough sleep. But if you ever get that the eigenvector is 0, you need to stop and give your head a shake and either figure out if you've got the wrong eigenvalue or if you made a mistake doing the elementary row operations. Okay. So the point is, there are only 2 values of lambda for which you're going to end up with a row of zeros. Any other value of lambda, you will get that A minus lambda I is row equivalent to the identity matrix. And the point is, if you have a 2 by 2 matrix, when you compute that determinant, you get a quadratic polynomial. And a quadratic polynomial is only going to cannot have 3 roots. It's going to have 2 roots. Are there questions? So let's do another example. Okay, so let's do a 3 by 3 example. Find all eigenvalues and eigenvectors of the 3 by 3 matrix 3, 1, 1, 1, 3, 1, 1, 1, 3. So step 1 is find eigenvalues. Find the eigenvalues. So that means we need to compute the determinant of A minus lambda times the identity. That is the determinant of 3 minus lambda. Okay, so when I write down A minus lambda I, this is going to look just like A everywhere except on the diagonal, right? Because lambda I is 0 everywhere except on the diagonal. So years of experience have taught me that when I do this, especially if the matrix has any negative signs and there's any risk of copy error, that the very first thing I should do is just write down all of the non-diagonal stuff, because that is stuff that I can do without thinking. Now I can write down the diagonal stuff. This is going to be more important when computing the eigenvalues, eigenvectors, but it's just a good habit to get into to avoid copy errors. Now, if this were just a matrix full of numbers, I would be inclined to try and do some elementary row operations to introduce some zeros. And I could if I'd like. So I'm not going to mess with this, because if I tried to use this 1 to clear this out, then I would have to subtract 3 minus lambda times this minus that to clear that out. But I could at least clear those out if I'd like. So I have 2 options. One option is to just compute the determinant straight ahead. The other option is I could try to introduce a 0 and then compute the determinant. For a 3 by 3 case, I usually just go straight ahead. But it's totally up to you. If you'd like, you could just say that this is the determinant of 3 minus lambda 1, 1, 1, 3 minus lambda 1. This minus this is 0. This minus this is lambda minus 2. This minus this is minus lambda plus 2. So So I can do that if I want. I don't usually do it, but I've just done it for you. Let's make sure I didn't make any mistakes. 1 minus 1 is 0. This minus this is lambda minus 2. This minus this is 2 minus lambda. Fine. So now my determinant is going to be 3 minus lambda times the determinant of 3 minus lambda, 1, lambda minus 2, 2 minus lambda. And now I'm expanding about the first column. So I'm going to have minus 1 times the determinant of. So I block out the first row and the second column, the first column and the second row. And I get 1, 1, lambda minus 2, and 2 minus lambda. So this is 3 minus lambda, okay, times 3 minus lambda times 2 minus lambda minus lambda minus 2. And then minus 2 minus lambda, or 1 times 2 minus lambda, minus lambda minus 2. All right, now at this point, I have a choice. One option is to just grind through, and I'm going to end up with some polynomial of the form minus lambda cubed plus something something. And then I'm going to try and factor. That's one option. The other option is to see whether I can factor before I continue. Because ultimately I would like to get that this is, minus lambda times something, lambda minus something, lambda minus something. Given that my goal is to write this thing as lambda minus something times lambda minus something times lambda minus something, plus or minus, are there any lambda minus somethings that I can simply factor out? 2 minus lambda. So 2 minus lambda shows up here. It shows up here. It shows up here. It shows up here. So this is just experience. You get this far and you stop and think. If nothing leaps out at you, you really do need to continue. But if something leaps out at you like, 2 minus lambda or lambda minus 2 is showing up in every single term, take advantage of it. So here I have 3 minus lambda. And in the first term, I have 2 minus lambda times 3 minus lambda. And what's left over from pulling out the 2 minus lambda? Minus what? Minus 1. And here I have minus 2 minus lambda, 1 minus So what did this leave behind? Minus 1. So here I have 3 minus lambda, 2 minus lambda, times 3 minus lambda plus 1, minus 2 minus lambda times 2. So this is 2 minus lambda times 3 minus lambda times 2 minus lambda minus 2. So here I just pulled that 2 minus lambda out, which was my goal. I left behind a 3 minus lambda. This became a 2 minus lambda. This became that minus 2. 2 minus lambda times. Now at this point I have to actually expand out. So I get 6 minus 3 lambda minus 2 lambda is minus 5 lambda. Minus lambda times minus lambda is lambda squared. Here I have minus 2. So this is 2 minus lambda times lambda squared minus 5 lambda plus 4. So I have that the determinant of A minus lambda I is 2 minus lambda times lambda squared minus 5 lambda plus 4. At this point, I could use the quadratic. Yes?
You make a mistake.
Probably.
Minus lambda plus 4 should be 4 minus 4.
Hold on. Here?
Yeah, 3 minus lambda plus 4.
Oh dear. What? No, that's certainly 3 minus lambda. This is 4 minus lambda. Oh, that doesn't make me happy. Okay, let's, but it's good that someone in the room can add small numbers. Okay, let's do this out again. 3 times 4 is 12. Minus 3 lambda minus 4 lambda is minus 7 lambda plus lambda squared minus 2. So that is 2 minus lambda times lambda squared minus 7 lambda plus 10. And this is, for me, a miracle, because the thing that I had wrong factored nicely, and the correct answer factored nicely. And so I was about to be happy because my wrong answer factored nicely, and the very fact that it factored nicely meant it must be right because it was a problem out of a textbook, and they always work nicely. And so I was about to go off and get something completely wrong because I had the blind luck that an arithmetic inability to add 3 and 1 correctly led to something that factored nicely. So usually when you make a mistake, if it's a problem from a math book or on a math test, your mistake will lead to something gross. In real life, things never are as pretty as they are on tests, and so you'll not be able to notice that you must have made a mistake because you got something gross looking. Anyway, 2 minus lambda. This thing we can factor lambda minus 5, lambda minus 2. So, first of all, what is the degree of this polynomial? 3. And the reason it is 3 is because the size of the matrix is 3 by 3. If you had expanded it all out, you would have either had to remember the cubic polynomial, the cubic formula. There is a cubic formula like there's a quadratic formula. Or you would have had to have made guesses at solutions and then factored them out using long division. In any case, we have 3 eigenvalues. 5, 2, and 2. 5 has algebraic multiplicity 1, and 2 has algebraic multiplicity 2, which is to say it shows up twice. 5 shows up as a root once. 2 shows up as a root twice. Whenever you get an eigenvalue with algebraic multiplicity more than 1, you need to be careful and nervous, because you might not get enough eigenvectors. Something interesting might happen at the level of eigenvectors. Anyway, we're now trying to find the eigenvectors. So step 2, find the eigenvectors. So first we'll do lambda equals 5. So we seek non-zero solutions of A minus 5 times the identity times x is the 0 vector. So I write down the augmented matrix. It's right there. Now, I'm going to be subtracting 5 off of that diagonal. And you've already seen that I'm not always reliable when it comes to adding and subtracting small numbers. So I'm first going to copy over the off diagonals before I attack the difficult problem of adding and subtracting small numbers. I need to subtract 5 off the diagonal. 3 minus 5 is minus 2. And I'm grateful that that's 2 more times. So that's what I have as my augmented matrix. Now, in the privacy of my own office, I get that this is row equivalent to 1, 0, minus 1, 0, 1, minus 1, 0, 0, 0, 0, 0, 0. The fact that I have a row of zeros tells me, first of all, that there will be a non-trivial solution. If there were not a row of zeros, it would tell me that either 5 is not an eigenvalue, in which case I go back and I check, is 5 actually a root of that polynomial? If 5 is not a root of that polynomial, then I have to go and recompute that polynomial. Or I go back and I check, is 5 a root of the polynomial? If it is, then I can check my elementary row operations again. But one way or another, I did things right. And I get that x is t, 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 is t times 1, 1, 1. And if t is non-zero, x is an eigenvector with eigenvalue 5. Now, that was step 1. Step 2, and so step 2 was lambda is equal to 2. And here, my augmented matrix, first I copy over the non-diagonals. Now I subtract 2 off the diagonal, and I get minus 1, minus 1, minus 1. In the privacy of my own office, I get that this is, whoa. You did not just see me fail to subtract 2 from 3. This is where, have you seen Men in Black? This is why they created tenure. All right, so the reduced row echelon form of this, we don't even need to go to my office. For the privacy, we just get this. How many free parameters are there going to be? 2. So x is equal to, first of all, I would take s to be 0, I would leave t standing, and I would get minus t, t, 0. Here I would take t to be 0, and I would leave s, and sorry, minus t plus t. Here I would get minus s, 0, s. So that is t times minus 1, 1, 0, plus s times minus 1, 0, 1. So certainly I have that x equals minus 1, 1, 0 is an eigenvector. so is minus 1, 0, 1. This is actually an interesting case because let's check our eigenvectors. So let's check that we actually have our eigenvectors. So check our eigenvectors work. So let's first check the lambda equals 5 eigenvector. We have 3, 1, 1, 1, 3, 1, 1, 1, 3 times t times 1, 1, 1. T is just some little scalar. It can run out. 3, 1, 1, 1, 3, 1, 1, 1, 3 times 1, 1, 1. This is t times 3, 1, 1, 5, 1, 3, 1, 5, 1, 1, 3, 5 is equal to 5 times t, 1, 1, 1. So we see that no matter what the value is of t, that a times this thing equals 5 times this thing. So no matter what the value is of t, a times that thing is 5 times that thing. If t is 0, this was a really complicated way of saying that a times the 0 vector is the 0 vector. But if t is non-zero, it was actually sort of interesting. For lambda equals 2, we have 3, 1, 1, 1, 3, 1, 1, 1, 3 times t minus 1, 1, 0 plus s times minus 1, 0, 1. And this is going to give me t times 3, 1, 1, 1, 3, 1, 1, 1, 3 times minus 1, 0, minus 1, 1, 0 plus s times the matrix times minus 1, 0, 1. This is going to be t times minus 3 plus 1 is minus 2. Minus 1 plus 3 is 2. Minus 1 plus 1 plus 0 is 0. Plus s times minus 3 plus 1 is 2. Minus 3 plus 1 is minus 2. Minus 1 plus 0 plus 1 is 0. Minus 1 plus 0 plus 3 is 2. And this is Gesundheit. This is equal to 2 times t minus 1, 1, 0 plus s times minus 1, 0, 1. Am I happy? Yes. Because the matrix times that vector equaled 2 times that vector. A linear combination of eigenvectors will be another eigenvector as long as they had the same eigenvalues. To be clear, if I had v with eigenvalue 1 and w with eigenvalue 2, if I computed a times tv plus sw, I would get t times av plus s times aw. This would be t. What is a times v? V, because v has eigenvalue 1. What is a times w? 2 times w. So I would get 2 tv plus 2sw. Did I get that a times this vector is just some number times that vector? So is this some number times TV plus SW? No. You could try that to be 1, which would make this match up, but that would be wrong. You could try that to be 2, which would make this match up, but that would be wrong. So a linear combination of eigenvectors is another eigenvector if the eigenvectors you're blending have the same eigenvalue. If you blend eigenvectors with different eigenvalues, you're not going to get another eigenvector. You're just going to get a vector. Okay, so now a quick example. So A is 6, 3, minus 5, 4, 3, minus 4, 9, 5, minus 8. I get that the determinant of A minus lambda I is equal to lambda minus 1 squared, lambda plus 1. The eigenvalues are minus 1, 1, and 1. So minus 1 with algebraic multiplicity 1, 1 with algebraic multiplicity 2. When I look for the eigenvectors, when I look for the lambda equals minus 1 eigenvector, I start with, I'm adding 1 to the diagonal. Okay, so 7, 3, minus 5, 4, 4, minus 4, 9, 5, minus 7, 0, 0, 0, which is row equivalent to 1, 0, minus 1 half, 0, 0, 1, minus 1 half, 0, 0, 0, 0, 0. And when I look for the lambda equals 1 eigenvector, I end up with 1, 0, minus 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. So here, I'm going to get an eigenvector. And here, I'm going to get an eigenvector. So I'm going to get the eigenvectors are all of the form t times 1 half, 1 half, 1. Here, the eigenvectors are all of the form t times 1, 0, 1. I had a 3 by 3 matrix. But when I looked for eigenvectors of this, only one direction. So I was hoping, in this case, I got two fundamentally different eigendirections. Here, I got only one eigendirection. And this is something we're going to have to deal with. So that'll be Monday's lecture, just to warn you that this can happen.